Hello everybody. In this video we'll look at an example from section 3.5, and so we'll look at an example of a curve sketching problem which includes slant asymptotes, and so we'll take a minute to look at slant asymptotes as well. And so the function that we'll be considering in this example is g of x, which is this rational function here where we have a quadratic function on top and a linear function on the bottom. And first we'll want to figure out what the domain and the intercepts for this function are. So for the domain, we have a rational function, no square roots, nothing too complicated in this function. We just need to avoid having 0 in the denominator. So as long as x is not equal to 3, we're good. As for the y-intercept, that's when we set x equal to 0. So we plug in x equals to 0. And g of 0 is equal to -2. So that tells us that the y-intercept of this function occurs at the point 0, -2. For x-intercepts, that's when we set y equal to 0. So we set y equal to g of x equal to 0. And so this function is equal to 0 when the numerator is equal to 0, x squared minus 2x plus 6. And you could try to factor this, and it probably won't work out because when you use the quadratic formula, you see that there are no real roots for this quadratic function. And so there are no x-intercepts. There are no values of x that make this equal to 0 or the function g of x equal to 0. Next, we look at asymptotes. And so first we look for vertical asymptotes, and vertical asymptotes will occur at values x that make the denominator equal to 0 while the numerator is not equal to 0. So here if we plug in x equals 3, what we see is that we'll get 9 over 0, putting this equal sign in quotes because this isn't quite true because 9 over 0 is not defined. But this is exactly what we're looking for to say that there's a vertical asymptote. And so at the line x equals 3 is a vertical asymptote for our graph. For horizontal asymptotes, we'll look at the two limits at infinity as x goes to positive infinity or as x goes to negative infinity of our function. And both of them will be infinite. So neither one of these limits actually exist. And that tells us that there are no horizontal asymptotes. There are no finite values which our function is approaching as x goes to positive or negative infinity. And so since there aren't any horizontal asymptotes, there is a chance that we have slant asymptotes. And are there slant asymptotes? Turns out yes. And we'll see that the slant asymptote for this function, for this graph, is y equals x plus 1. So how do we know when to look out for slant asymptotes? And so it's a matter of, if we know that our function goes off to positive or negative infinity, as x goes to positive or negative infinity, there is a chance that we have a slant asymptote. And something to look out for, like a little hint, if the degree of your numerator is equal to the degree of the denominator plus 1, then there's a good chance that you have a slant asymptote. So an alarm should go off in your head like, hey, maybe I should look for slant asymptotes. And so if we look at our function g of x, so we have quadratic on top, linear on the bottom, some alarm should go off on our head because the degree of the numerator is exactly 1 more than the degree of the denominator. And so there's a good chance that we'll have slant asymptotes. And to find those slant asymptotes, to figure out what that line is, we want to find numbers m not equal to 0 and b such that the limit as x goes to positive infinity or as x goes to negative infinity of our function minus this linear function is equal to 0. So here m is our slope of the line and b is the y-intercept of that line that defines the slant asymptote. And so if we look at this, it's saying that our function gets really, really close to this linear function as x gets really big, which is another way to say that the graph of our function will get really close to the line defined by this linear function. And now through the modules, there are two different ways that we've seen to find slant asymptotes. The first is polynomial long division. The second involves these limits at infinity to figure out what m, the slope, and b, the y-intercept of the line defining the slant asymptote are. And so let's take a look at this. Let's show that the slant asymptote actually is y equals x plus 1. And first let's do it through polynomial long division. And note that we can only use polynomial long division if both the numerator and the denominator of our function are polynomials. And so to do this polynomial long division, let's recall, so we'll look at this x squared and we'll ask, okay, what do I need to multiply x by to get x squared? Well, that's not so bad. We just need to multiply by x, and then we multiply x by the whole divisor, so x squared minus 3x. We negate both terms, and then add together or subtract. So the x squared terms will cancel out, and we'll be left with x, and we bring down the rest of the polynomial. So this 6 travels down. Now we have x plus 6. We do the same thing. We ask, okay, what do I need to multiply x by to get x? Well, that's not so bad. That's just 1. So plus 1. Now we multiply 1 times the divisor, so x minus 3. We negate the whole term. And now we add or subtract, and what we're left with is just 9. And so our remainder here is 9 divided by x minus 3. And so what's the takeaway? The takeaway here, our function g of x, which is x squared minus 2x plus 6, divided by x plus minus 3, that's equal to x plus 1 plus 9 divided by x minus 3. And then we, this isn't super formal, but we can kind of look at this and say, okay, as x goes to positive infinity, and we take the limit at infinity of g of x, what we'll see is that we will look at like this line x plus 1, because this 9 divided by x minus 3, as x gets really, really large, this term is going to get really, really small. And so our function is going to get really, really close to this linear function. The second way to find slant asymptotes is using limits at infinity, and this method will work more generally, even if you don't have a polynomial in the numerator and a polynomial in the denominator. You can use this method to find slant asymptotes when they exist. And our goal will be to find the slope m and the y-intercept b of the line which defines the slant asymptote. And we can find m by taking the limit as x approaches infinity or negative infinity of g of x divided by x. And so we'll take that limit of our function divided by x, and then we remember, okay, dividing by x is the same thing as multiplying by 1 over x, and so this is the same thing as the limit as x goes to positive infinity of x squared minus 2x plus 6 divided by x minus 3 times x, or x squared minus 3x. And now this is similar to the types of limit at infinity problems we've been looking at in class. So we'll divide by the highest power of x, which appears in the denominator, which here is 1 over x squared, or here is x squared. And so distributing out that multiplication, what we're left with is 1 minus 2 divided by x plus 6 divided by x squared divided by 1 minus 3 divided by x. And we remember that theorem, or we think, and we see that as x gets really large, 2 divided by x gets really small, and whenever we have a finite number divided by a positive rational power of x, that term will go to 0 as x gets very large or very negative. So these terms all go away, and what we're left with is just 1. So this is our slope m. To find b, the y-intercept of that line defining the slant asymptote, we will now take the limit as x approaches infinity of our function minus mx. So we need to use the m that we just found above. And so this is the limit as x goes to infinity of our function x squared minus 2x plus 6 divided by x minus 3, and then we want to subtract away x. And to do this subtraction, we'll want a common denominator. And so this is the limit as x approaches infinity of x squared minus 2x plus 6 divided by x minus 3 minus x times x minus 3 divided by x minus 3. With this common denominator, we can now do the subtraction. And what we get left with is just x plus 6 divided by x minus 3. We evaluate this limit at infinity the same way we have been, and in the end, what we should end up with is 1, and so this is our b. And so we can conclude that our slant asymptote is y equal to mx plus b, which in this case is y equal to x plus 1. So we end up with the same line that we found using polynomial long division. We haven't used the first or the second derivatives yet, and so we want to make use of these derivatives. So first we figure out where our function is increasing versus decreasing. We locate our local max and min points. And so we first compute the first derivative, and we can find the critical points. So we can find the critical points where the derivative is equal to 0, which are x equals 0 and x equals 6. And also we notice that at x equals 3, the derivative does not exist. So we have 3 critical points. We use those to divide up our real line into these subintervals, and then sparing you the effort of plugging in, we can see by plugging in some numbers on each of those subintervals, we find where the function is increasing versus where it is decreasing. And once we've done that, we can also determine whether our critical points are local max or local mins. We can find the values of those local max and min points to write them down as ordered pairs. And we note that at x equals 3, we already said that we had a vertical asymptote, so that will not correspond to a local max or a local min. For the second derivative, we compute it. We notice there are no points that make the second derivative equal to 0, but there is a place where the second derivative does not exist at x equals 3. We use that to break up our interval into 2 subintervals. We plug in to check the sign of the second derivative. We see that it's negative on the left to the left of 3, positive to the right of 3, corresponding to concave down and concave up, respectively. And we don't have any inflection points, but because we remember, okay, at x equals 3, we just have a vertical asymptote. Great, so now we have used the function itself, the first derivative, the second derivative. We've learned a lot of information about this function and its graph. We're ready to draw a sketch. And so first we remember that we found a y-intercept at 0, -2. No x-intercepts. We found a vertical asymptote at x equals +3. And we found a slant asymptote of slope 1 with y-intercept 1. So it would look something like this. Cool. And then from the first derivative, we learned about a local max at 0, -2, which we've already plotted. And we found a local min at 6, 10, which would be around here. And so 6, 10, and 0, -2. And then we use the increasing decreasing test and the concavity test to mark on which intervals we're increasing or decreasing, where we're concave down and concave up. And now it's just a matter of plotting this graph. So we know for very negative values of x will be very close to this line, our slant asymptote. We're going to be increasing in a concave down way until we reach our local max. And now we start decreasing, still in a concave down way, and we approach our vertical asymptote. To the right of x equals 3, we'll be decreasing, coming down along this vertical asymptote until we reach our local min at 6, 10. We remember that we're concave up over on this interval, and then we start increasing in a concave up way, and for large values of x, we should get close to our slant asymptote. And that's it. We now have a pretty good sketch of our graph of this function that we probably didn't know the shape of before we started this problem. Thanks for watching.